Okay, I'm going to get started. I'm Colin, also from Berkeley. I'm going to be talking about the VLSI flow we developed at Berkeley to help us tape out a bunch of chips that you saw in the chipyard presentation. We call it HAMR, which stands for Highly Agile Masks Made Effortlessly from RTL, but you don't need to remember that. Okay, so Alon or Sagar, I forget who showed the slide before at lunch with all these chips, and it's kind of lost in this, but the chips on the far right are roughly like 20 times bigger than the chips on the far left, so we're increasing not only the amount of chips we tape out, but also the size of them physically. And so in order to get all these chips out and have them working, booting Linux like Sagar was talking about, we need to do real VLSI work to get everything going. And we don't have a lot of people, so how do we do that? A lot of people like to, when you learn maybe VLSI flows at the beginning, you just think of it as this, kind of two-step process. You just have synthesis with tickle scripts and standard cells, and then they produce gates that get placed and routed, and you get a chip out, and you're done. And unfortunately, that's not how it works. Obviously, it's not that easy. Otherwise, there wouldn't be so many people working on this. So what is a real VLSI flow? This is just, I don't expect you to read all this stuff, but there's all these different steps that happen where, you're going to get a new PDK from the foundry, or you're going to get cells that are broken, or you're going to run synthesis and it fails for unknown reasons. So there's a whole bunch of iterations that you're going to go through, a bunch of trial and error steps you're going to have if you just start bringing up a VLSI flow from nothing. And that's what a real VLSI flow is, all this extra stuff that you have to do to get it to work. And so, just one second, sorry. Okay. Basically, we see how this has worked at Berkeley in the past was basically for each chip, we would copy over the scripts from the old project and basically start rewriting everything ourselves. But that's not really a good software engineering practice, right? We should be trying to reuse the different components of the flow that we've already built before that we know work, and kind of pass the information forward and just keep steadily improving our VLSI flow. So that's why you have all these different, the reason that's troublesome is because you have all these different concerns kind of mixed into your VLSI flow by default. So you have tool concerns, which is things like your CAD tool vendor changing or the version of it changing, features being broken in different versions, all sorts of problems with that. So we'll have different file formats for different tools or different library types they expect and work with. But there are also this green box is process technology concerns, which is things that are specific to your process technology, what the SRAMs look like, things you need to work around for DRC rules or other such technology issues. And then the last concern is this, your design concerns, which is what hopefully you want to spend most of your time working on, what's the floor plan for my design look like, how many power domains do I have, where are all the clock domains, things like that. And so kind of the idea behind HAMR is to help separate out these. So in a traditional flow, we have this, you kind of just shove all these things into one big file, one big large tickle script, or maybe it's several tickle scripts, but they kind of intermix these concerns freely with no thought for reuse or modularity. And so HAMR's real idea is to try to separate these out. But why does this have to be a complicated process? Well, basically, designs continue to get bigger. As I was talking about before, the first chips we taped out of Berkeley were these single core chips that could, fit in a square millimeter. Now the last chip we taped out is, 56 square millimeters and 20 cores with all sorts of fancy bells and whistles. And so the similar trends continue in industry. More and more transistors means more and more design complexity, and designs keep getting bigger. But also, as I was talking about, with the tool concerns, the EDA industry continues to evolve, continues to produce new tools for different things people care about nowadays, with lots of different file formats they expect, different different command line arguments, things like that. And they kind of pay lip service to making common exchange formats, but they don't really end up with like a common API that you can code to for across different tools. And then the real reason that this becomes complicated, as I was talking about, is just the mixing of all of these concerns together means that you have kind of just a mess of all this stuff with no chance of reusing it. So before I go into the subtleties of how we solve the last two problems, I just wanted to quickly touch on the large designs. So Hammer supports hierarchical design, which is a pretty common technique today where people are building large chips by hardening smaller components like a core or a cache and replicating them across the chip. Just because the number of transistors you're putting down is prohibitive for this, NP-hard problem of place and route to ever finish. So you divide and conquer. This isn't a free solution. There's a lot of work that goes into hierarchical design, but essentially, Hammer helps you solve these problems in a more tractable way, and we'll talk a little more about that at the end. But I'm going to get more to the crux of Hammer, which is this last set of things, kind of how do we do this modularity, and how do we do this reusability. So this is an example of something you might see in your magical tickle script, right? So here we've color-coded these parts of the words in this command that are for the different concerns I was talking about before. So this is just a series of 3 tickle commands that are setting options and then making a single power strap for one layer. And so the orange stuff is all these CAD tool specific and command line specific options for a specific CAD tool. So that's most of it. But then you're also mixing in things that are technology specific. So the name of the metal layers is written here in text, and the exact spacing you need between metal layers is another thing that's based on technology. And this helps you get to your DRC clean and get you the right power delivery you want for your power straps, but it's intermingled with all the rest of this stuff. And then we also have some blue words here, which are your design specific criteria. So the name of your power and ground, how many straps you want per millimeter, and the name of some of your modules that you're putting the straps over top of. And so all of these get mixed up into one line of code, and there's no real good way for you as the consumer or producer of this file to separate them out. And so Hammer is trying to attack this problem by making it easy for you to basically generate these scripts and not worry about the different concerns all at once. So as always, the solution in computer science is to add another layer of abstraction. So we basically come up with 3 categories of flow inputs based on the 3 concerns we have. So you have design-specific stuff, which, as I was mentioning, is things like your floor plan, the name of your clocks, the speed of them, the hierarchy of your design. Then you have your tool/vendor-specific settings. What tool do I want to use? How do I generate tickle for that? What file formats does it expect? And then there's technology-specific flow input, which is, where are my actual libs and lefts, or where are my standard cells, what's the metal stack-up of my technology, things like that. And so Hammer's goal is basically to specify all 3 of these flow inputs separately. This allows you, me to reuse someone else's tool plugin or someone else's tech stuff on my new design, or share my design with someone into a new technology or tool. And it helps kind of reduce the amount of things you need to know about in the VLSI flow. You don't need one super expert who knows the whole entire Magic Tickle script and how to change everything about it, including your design. You can get someone who's an expert in a specific tool to help add an API or another abstraction for Hammer. So digging down a little bit into these different boxes. So as I was mentioning, design concerns include things like floor plan, your physical hierarchy, where your pins are on your blocks for your hierarchies, other placement constraints for macros or whatever. It also includes, your clock constraints. This is frequencies, input-out constraints, pin delays, things like that. Also design modifications like what you want retimed, how do you want to put your scan flops in, and all of this stuff is what we consider design concerns. And so we're storing these in an intermediate representation in Hammer, which is basically YAML JSON kind of language. And we're emitting this from some higher level input sources. So, fertile annotations can end up emitting Hammer AR or other, TISL level annotations even if you wanted to. And then Hammer is consuming this intermediate representation to produce these toggle commands that encapsulate all of your changes. Hammer is also able to, perform quality checks on your IR to make sure you're not doing anything dumb or something that will break the tool. So you don't need to wait for a whole tool run to figure out if you just have a syntax error. But in order for this to work, we need what we call tool plugins, which translate from this IR to the tickle that the tools consume, or whatever language. And so this leads into our tool concerns. So some of the things here are pretty simple, like where do my cadence tools live? Where's my license server? What version do I have installed? And these are all overridable in Hammer by configuration files, which look pretty much like IR. They're YAML JSON. And then we also have, but the real meat of the tool concern is how do you, draw a power strap in Innovis, or how do you draw it in ICC2, ICC, things like that, right? Is how you convert from intent to a specific tickle command. And it's really difficult because they're not standard across vendors, and there's really no commitment for the vendor to ever support support these APIs for more than one version. So things will break randomly. You might have to update versions and change half your scripts. But so the solution here is we're implementing basically Python methods that consume this IR and emit tickle. So this lets us have kind of an API where, this is what a place and route tool should do, and if you encounter this step in the IR that you need to do, your different subclasses of that tool can then, there's an Innovis subclass and a ICC subclass, and they can use the same input IR to produce different tickle, but in a nice abstract way. So there's a bunch of standard Hammer steps that we put into your flow by default. There's also vendor-specific steps, and there's ways to modify those steps, which I'll talk about a little bit later. Okay, and so then this brings us to the last of our three concerns, which are technology concerns. So the first set of stuff is kind of things that I like, similar to the basic tool concerns, which, where is my PDK, where are all the technology files, where are the name of my standard cells, what are the implement, where's my other IP, what PVT corners do I have available in this technology, or for my site. And then there's also technology-specific tickle commands and snippets. Basically, there's Python methods that include specific snippets for your technology. So let's say in your technology X, you need to run this particular step before you ever do a floor plan, or after you put down power steps, you need to run this special command to make sure everything's cleaned up correctly. And so technology, like this kind of technology snippets allowed to be included into your plugin itself. Okay, so I've been using this word plugin a lot. And so what exactly does that mean? We have two types of plugins, one for your tools and one for your technologies. Basically, we separate them in our directory structure with, the action they perform, so place and route or synthesis, and then the name of the tool itself. And these all contain a pretty standard set of things. So we have this defaults.yml, which is basically this list of IR variables or settings that you can set for the tool. And it lists, that's where also kind of where the documentation lives. It says, what this parameter does and how you can set it, or the possible settings that you could override it to. And then the core chunk of it is this, init.py file, which is basically the reusable Python methods that translate from a specific Hammer API to tickle code. Then technology plugins, on the other hand, they also contain a defaults.yml, which has a similar set of APIs for technology overriding. Also, this JSON file, which points to your PDK files and other things. And then we have these reusable Python methods that inject technology-specific stuff. And so here you can see it's a little more complicated because we need to not only name the technology, but the tool that this reusable Python stuff applies to, because there's not really a way to separate these entirely. Okay, so what does this hammer adder look like? We've got a little simple snippet on the slide here. It's basically this YAML description, and it can override either these default text settings or these default tool settings that exist in the other defaults.yaml. And it has these namespaces. So on the top line, line break there. You can see that's VLSI.inputs.clocks, and that's showing you we just have a single clock in this design that operates at 1 nanosecond with a 0.1 nanosecond uncertainty. So the namespace is basically your VLSI for general settings. Then we have things like core, which are the whole tools, the whole hammer flow changes, or inputs, which is what kind of things we're giving to the tool. I won't go through all of these yet. Okay, so that's like the whole gist of Hammer, but what does it actually help us do better? So this is one problem that we worked on in Hammer to make it easier to actually elevate, like give you a good API that's useful, more useful than just writing tickle scripts yourself. So power straps, something you need in all your digital designs. And it's really hard to get them exactly right, especially when you're doing things like hierarchical design. You have to make sure you're getting the DRC rules correctly, so you're not putting your power straps too close together or too wide. You also need to make sure you have enough power straps to meet your target power dissipation. You know, if you're going to burn 10 watts in a small area, you need to have a lot of power straps. You also might have a specific IR drop spec you're allowing for, 10% or 20%. Whatever it may be, and that's going to change exactly how many power straps you put down. And then you're also going to have, where are my power domains? Which ones are switchable? Which ones change? That also affects your power straps. And so, as I was mentioning, hierarchical adds even more constraints because you're going to need to have, some pitch matching of these straps across tiled modules, and it's easy to make mistakes when you try to do this back calculation to figure out I'm going to meet all these different pitches and all these different rules and try to just, write down exactly how many nanometers wide my wire should be is not easy. And so Hammer adds the ability, it adds an API to avoid making you do this math over and over again. That's tech and tool specific. And so Hammer does this in basically this method of determining the valid pitches, then calculating the offsets based on, your other hierarchical blocks, and then generates these DRC clean straps for you. It's also, so because we're doing it at this higher level, rather than just widths and spaces, we're using this by track specification. I think this is a common method that a lot of people use for power straps. You're trying to put as many down as possible without using up excess routing tracks. And so here we're going to say, this is Hammer IR in the bottom right. It's showing, we're going to say for place and route, generate power straps by tracks. And then we say, okay, so for our by track options, we want power and ground width of four routing tracks. And we want 50% of our routing tracks to be used for power and ground. So once this is specified, then Hammer can figure out what the pitch should be based on the number of power nets in your design and these two numbers. So notice we didn't have to tell it. We have VSS and VDD that's specified elsewhere in the design. It just knows that because it's smart. And then you say, how many layers which layers do I want my power straps on? So this assumes that, you can connect from M3 down to the standard cell rails. And then we have alternating, or we have layers going all the way up to M9, which might be the top layer. This allows it to generate straps. And then because because it's doing this calculation with all the tech parameters and tool parameters that it has, it does this optimal thing where you can have, you can use all these routing tracks even right next to the straps. So on the left, we have an example of this where we want a 10% utilization. But then when we increase to 30%, you can see Hammer. You don't have to change any number other than this, and you get this nice regular DOC clean grid with 3 times as much power utilization. Okay. So now that you see a nice feature Hammer has that you might want to use, how do you go about it? So Hammer is now packaged in Shipyard for ease of consumption. So it's in the VLSI folder, perhaps obviously, perhaps not. And so for various reasons, we can't just put all of our tool and tech plugins on the internet for free, but that's just the world of physical design. But you can message us. I have links at the end of this talk to email us for access to the tool and technology plugins. If you happen to have the same access on your campus or wherever you work, you can get them as well. And so the primary use case for this tool was basically, building that series of many chips that you saw before. Bug. We are not working on open source alternatives proprietary CAD tools. That's a different project. Yeah, so, and since real technology is needed today, there are fake technologies that we use, and so in the Shipyard repo, there is an open source tech plugin based on an open source technology. I don't like the slide.
Okay.
Yeah, sorry. So I'm going to walk through what a demo would be. We don't, as I mentioned before, it's hard to just give everyone access, so you guys won't have Cadence tools on your laptops, but I'm going to walk you through a demo that pushes a SHA-3 accelerator from Shipyard through Cadence and Mentor tools to generate DRC LVS clean design with Hammer relatively simply. It's using this ASAP7 predictive PDK. You can read the disclaimer on there, and it kind of walks through how you use Hammer from Shipyard to run the CAD tools, but it doesn't actually run them, and if you want, you can email me to get this little tarball that we have, assuming you have the right licenses. Yeah, so basically, we're trying to show this reusability of Hammer, so you can put this accelerator through a simple physical design process with just pulling in all the stuff that's already written in Hammer and all the plugins that are already written. You don't have to write pretty much anything yourself to do this demo. So we're using the ASAP7 plugin, which is basically one of the only plugins that's open sourced. So that path works in Shipyard. And then we also pull in a bunch of tools. As I was mentioning before, we use Cadence tools for synthesis and placement route with Innovis and Genus. And then we also have Synopsys for VCS simulation, and the Mentor plugins for running Caliber to do DRC and LVS. And all of these are already written, and we're just, mixing them in. So as I was mentioning before, we're just going to pull in these plugins, has all these stuff in them. So what does that look like? How do we note that? So this is how we specify the ASAP7 tech plugin. You can see Hammer supports the concept of stack up, which is how many metal layers in which directions and of various widths do you have. We have that for other technologies as well. You have to tell Hammer where the standard cell layer is, or where the standard cell rails are. In this technology, they're in M1. And then something to use to stamp out those standard cell rails. There's a bunch of other kind of low-level technology stuff there you have to specify. But this is all kind of inherited from the ASAP7 default YAML. You can see at the bottom, that's the path. So if you want to create a new one of those, you should contact us or read the docs. We have the documentation set up already. I'll have links to everything at the end as well. Here's some more of the stuff we're using. So this is an example of what a tool plugin might look like. How do you initialize the environment for some tool? You're gonna set a bunch of variables, look at, based on the design you have, is it hierarchical, is it not? What kind of libraries do I have? You're gonna emit a bunch of different tickles. And so this isn't an actual tool plugin, but here's what looks something like this. and we're just pulling in all of this Python code to generate the tickle scripts. Again, if you want to implement a new CAD plugin, first check with us to see if there already is one existing, and you can just contribute, or you can read the docs. Okay. So how are we going to specify the design that we need for this SHA-3 accelerator? This is kind of what we see as the meat, the part you want to spend time on is specifying your constraints for your design. And so this is things like, in this example, we would have, some IP, analog IP, or some other hard macro that you need to integrate. In this one, there's a, black box CCO. You're going to have floor planning information, clock and power, how the hierarchy works, and then a little bit of boilerplate to select what technology and tools you're using. So in Shipyard, the VLSI example project structure looks looks pretty straightforward. There's an example VLSI script, which is basically like your main, and this is just a small wrapper around Hammer VLSI. And you have your example.yml, which includes your project-specific Hammer IR, as well as an extra libraries folder, where you would put your macro collateral. Basically, everything's put in example.yml, but you could separate it out into example tools, example tech, example design, whatever. You can add arbitrary number of YAMLs to your Hammer VLSI invocation. And so then, basically to run Hammer, to have it run its flow, you're going to give it your YAMLs and then give it an action to take. And this one we just have, the example.yml and syn, which is synthesis. But you can put par, you can put auto is the fancy one that just, looks at your whole flow and tries to run everything to the end. And talk more about those in a second. So looking at what your example.yml might look like to select your ASAP7 technology, you're just pretty straightforward, pointing it to ASAP7. This assumes that there is a folder called ASAP7 in one of your paths, and then you'd have to specify where you've downloaded the ASAP7 tarball to then Hammer will automatically extract it, put it in all the right places, and be able to use it. We also have to select what tools we're going to use, because you could have a bunch of different plugins, and you might want to push it through, cadence tools or synopsis tools. In this yellow part, we've selected genus for synthesis. So basically, again, you're specifying the name of the tool, which corresponds to, and then a path to that directory that contains that tool. And then we also set the version that we want to use. Hammer supports a wide variety of tool versions and has a nice API to determine what version your tool is and to appropriately emit the right tickle command to avoid that whole problem that we talked about earlier. Then we select Innovis for place and route, and Caliber for DRC and LVS. There's little notes here about okay, so then going into more of our design collateral. So this is a simple design, so we just have one clock called clock. Looks similar to what we showed you before, 1 nanosecond period, 0.1 nanoseconds uncertainty. This bottom part shows a nice little bit of Hammer API where it'll do a power specification for you, assuming you have a reasonably simple design. So you can just say automatically add a CPF, and Hammer will generate that for you as collateral and give it to the tools at the right times. Looking at a little bit of a floor plan. So this is kind of our low-level floor plan API, which is just Hammer IR. In yellow is the top level of the design. So this is, a whole SHA-3 accelerator with that DCO black box, just, 300 by 300 with no margin on the outside. So this is something that's designed to be integrated as a subcomponent. Then in blue, we show another feature so this is adding an obstruction at the bottom for DRC reasons, something you might have to do in real physical design. And then the green box is that hard macro that I mentioned. We're integrating this DCO placed at a fixed location with a fixed width and height, and that's in green. As I was saying, this is designed to be integrated into a larger flow, so we need to tell the tools where to put the pins on the outside of our block. And so here we're using another Hammer API for pin placement, basically saying this is semi-automatic because we're going to give some feedback to the Hammer about what we want the pins to be. And so here we're saying, put all the pins, that's what the star is, on layers 5 and 7 at the bottom of your block. And so then Hammer just automatically does that for whatever tool you have correctly. And also with correct DRCs for your technology. Oh yeah, so this is power straps. We've went through this pretty detailed example. So this is what the SHA-3 power straps would look like. The only difference here is we're specifying a few more overrides. Power straps have this, the Power Straps API has this nice ability to override for specific layers. So you can say, kind of at the bottom here, we see power utilization is 5% normally, but on metals 8 and 9, we have basically a full dense grid for the maximum amount of metal for power on the top layer. Then we have how you would include, your analog or hard IP or hard macros. So at the top, we're saying we're going to have extra libraries appended from this file. And here is the extra libraries we have. So we specify, things like where the lib file is, where the left file is, where the GDS is, and then also, the PBT corner. This is a slow. This lib is characterized as slow at 100C, and these are the voltages that it's running at, or this is the voltage that's characterized at. And then at the bottom, we basically, because this cell isn't real, it's just a physical only cell. We don't have any behavioral stuff or any other details of it, so we just add it to this physical only cells list. And then we're just going to place it inside with the floor plan that I showed before. Okay. So another key principle of Hammer's design is to be able to incrementally move to this flow. You don't have to wholesale delete all your tickle scripts and use Hammer because we thought pretty much no one would buy it if we did that. So we have what's called hooks, which are your ability to add in a little bit of tickle script from past success you've had or an old flow that you're porting over. So you can put this bit of tickle into a hook and then have it run before, after, or instead of particular Hammer steps. So if you have a floor plan step already done and you don't want to use Hammer's abilities, you can just replace it with your own Python or tickle script, basically. This allows kind of the quick and dirty, I'm trying to tape out right now, I need to fix something in my flow and I can't be bothered to make an API PR to Hammer. And then it also, because you're able to quickly integrate it and kind of put it in the right place in your flow, you can eventually use this as kind of like a prototyping area. So kind of in our flows with tape outs, it's been, first it's just a one-off hook, and then next time it's a prototype API, and then it's a stable API across tools later. So that's helpful for us in expanding the capabilities of Hammer and not forcing users to delete all of their old tickle. So as I was mentioning before, you can have technology-specific hooks. So ASAP7 has this weird thing where in order to get around licensing issues at very low nanometer nodes, it generates upscale GDS that you then need to scale down yourself. And so the ASAP7 technology plugin provides a way to automatically do this so that when Hammer's done with your ASAP7 run, it just has normal looking GDS. And so we have this scale final GDS hook that gets run and at the end of write design, which is when Hammer would normally finish, but instead in ASAP7 it does this extra script call to do the scaling for you. So this is just an example of something you can add that it's a weird technology thing like they all have. And then in order to actually have it added at the end, we're going to ask Hammer to make a post insertion hook. So after write design happens, call this other function scale final GDS. This is kind of a look at what your example VLSI will look like, where you're adding, your own custom hooks. Another nice feature of Hammer, something you might expect, is that it can generate a makefile with all these intermediate targets to avoid having to rerun everything from the beginning, or if you stop in the middle, Make will be able to figure out where, based on what's been produced thus far, where you are in the flow. And so you can set this build system parameter in VLSI core to Make. That's the only one supported right now, but it's an API that you could have any build system you wanted there. And then we also have nice things like LSF job submission commands. So if you have a compute farm that you want to farm off your VLSI jobs to, you can also do that. And then the nice thing is that once you run Hammer to build this makefile, you can run make-j DRC LVS, and Hammer will do your whole thing, fan out all the hierarchical subblocks, do as much parallelism as it can to generate your results. Okay, so now we're getting much closer to this kind of, type Hammer, auto, and basically this whole thing works. But if you want to run these substeps, we have, I was talking about before, basically you have synthesis, fin, that takes in your Hierarchical Design, which is Verilog, that's generated from Fertile, generated from Chisel, and then outputs your technology map scape level net list. I'm going to skip this because we don't have the folder for you guys to look at. You can also do the same thing with make-par. Basically, it takes the synthesis input and generates your GDS. We do have time for this, so this is actually a little video of the demo running. I don't know if this will work here or if we'll have sound. We don't need sound. So make build file is that command that I was talking about before that will generate the make file. So you type this, and then Hammer is going to elaborate. So when you're in the shipyard mode, Hammer will know to elaborate your chisel, run Fertile, produce the Verilog, and then produce a make file based on your example.yml and what kind of subsets Hammer needs to do. And if you type, /hammer, blah, 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 fin, you'll see this spew of CAD messages, and eventually you'll get your Hammer will output another little Hammer IR snippet that contains all the information it needs to carry over from the previous step to the next step. We didn't quite talk about this part, but there's transition commands for Hammer to ingest the old IR, produce new stuff for the next tool. So you can switch between tools if you wanted to, synthesis and synopsis and place and route in cadence land. You run make par again, or /hammer par. Takes a while, but eventually solves all your DRCs and you get GDS. And they accept every technology, then it has to do the scaling, and then it finishes. There's a handy script included to view your GDS in an open source viewer if you would so like. Obviously, it's not the best way to do it, but you can see the box in the middle is goes quite fast. The box in the middle is the black box with all the routing around it. You do the same thing you would do with the par output to start running DRC. So here we're switching tool vendors, right? So we're taking in the par outputs from Cadence and sending them into a mentor tool. It's pretty common, but worth noting that Hammer can do that. Get your DRC results, and then you can do the same thing with LVS. It's going to have to take in the par input to figure out what to give to the LVS tool, and then it'll fire up mentor, and you'll have your DRC and LVS results. I think the video's done. All right. Okay. So that's a whirlwind tour of Hammer and what it's currently capable of. So where are we going with the rest of Hammer? So kind of the idea of Hammer, one of the ideas is that it's good for generators, which is what we have in Shipyard. We have this wide set of designs that we can build, and we want to have a physical design tool that's equally capable of handling a wide set of inputs. So things that were currently in progress is, one of my colleagues, John, is working on this floor planning stuff, or sorry, you can already make floor planning scripts in Python that, auto-generate your placement constraints, but integrating that more directly into Hammer, John's working on. We also have Scala API, Chisel/Scala APIs to help tie your generator to your physical design. This is also working with some of the aspect-oriented stuff that Adam mentioned before, so you don't have to mess up, open source Rocketship or upstream whatever thing you have. You can just add these on the side as you normally do a floor plan. Checking these things against all your alignment constraints, whether it's your analog grids or your digital fins or whatever. We also have another student working on getting better clock constraints out of Chisel. So if you build a clock mux in Chisel, the tool, or you have a bunch of clocks input, the tool by default doesn't know that, and you have to encode that yourself in Hammer IR. But it seems pretty straightforward from our perspective to have these muxes produce the right bits of Hammer IR, which eventually produce the right bits of SVC. In general, closing this loop of reconfiguring your Chisel design based on physical design feedback is something that we're continually working towards making a tighter and tighter loop. We still need to add a few more sign-off tools to Hammer. Right now, we're just running IR drop outside of Hammer, and dynamic power analysis, well, it's actually pretty close to being done. And then, some more formal verification kind of things like LEC. And then we're always improving our physical design APIs, and feedback is welcome on those. So in summary, physical design is hard. You can't just push a button and have it go without a lot of work behind it. And as chips grow in complexity, it becomes even harder. And CAD tools are always annoying and difficult to deal with. So having someone else do it for you is great. So Hammer helps people share that pain and that burden and give other people reusable code and modular plugins. And we can show you, and we showed you how fast it is to get through a simple demo of something in Chisel from Shipyard. And so here's all the links I promised. It's included in Shipyard, and so there's basically you can walk through the same thing I just talked through on the Shipyard VLSI SHA-3 example. And then there's also Hammer's own read the docs, and if you would like access to the plugins, tech or tool plugins, you should email that listserv. And with that, I'll take questions. Yeah.
So you maintain the plugins for the tools?
Yeah, we do.
Okay. How do you keep those in sync with the different tool versions that come out?
So yeah, so we have I guess, inside of the tool plugins, you can basically query what version Hammer is running on, and then based on that, emit the correct set of arguments. And when the tool is updated, when somebody's using the plugin gets that update, they can, we can't really prefetch that without knowing what's in the new tools. They don't publish nice change logs, but then when something breaks, we have a little switch that says, for this version, we need to do this instead.
Right. Okay. So have you written all the plugins so far? Or
not specifically me. Berkeley people have written. Yeah.
Okay.
Yes, we have plugins that work from well, we only started kind of recently, so we have Innovis 17 up to Innovis 19 something, with a couple in between. Genus, obviously, along a similar range. We have some Synopsys plugins for older versions of ICC and DC. We have the Mentor plugins. We have a Voltus plugin in progress now. the VCS plugin. Yeah, you can, yeah, if you email that list, we'll.
Yeah, I'll talk to you later.
Sounds good.
How are those plugins available?
Yeah, so we have agreements with some of the vendors to share them with people who also have access to those tools. And so we basically have a way to figure out if, we ask them if you have access, and then we can share it with you. Yeah. The tech plugins are a little bit harder, but a similar system in place.
I have a somewhat broad question. What would you say, can you give some insights into the sources of productivity improvement that comes from following a particular agile design convergence? And is Hammer absolutely essential piece of that? And if so, how, for example, in an industry environment that already has a mature physical design tool, what would be the convincing reasoning to get them to adopt Hammer? What would you say?
Yeah, so to the first one, is it absolutely essential? I would say, basically, so we're starting to tape out lots of designs with few people, and I think at that level, you need to be able to share code with each other. So, for example, last 2019 June, we basically had 3 chips going out, cumulatively over 100 square millimeters. The designs are all separate, but it's on the same, technology, so we're able to share fixes with each other and basically pool those 6 grad students' efforts to work together in a way that reduces all of our effort. As to how would you convince some industry person, I agree that's a little bit harder of a sell, but that's kind of why we have this ability to incrementally adopt. You can use Hammer for some parts of your design, or you can, put your old flow into Hammer if you'd like. Edward, a Hammer developer, would like to say something.
Oh, and I guess to add to that, I think if you have a lot of traditional industry flow, what happens if you need to switch CAD tool vendors or switch architectures or switch technologies? Is like the typical industry flow going to be suitable for that? So I think an area where Hammer kind of really shows up nicely is that I have this existing flow, but I need to switch CAD vendors. Under the traditional methodology, that's going to be a huge rewrite.
Yeah. So it's kind of if you're moving fast to different things all the time, it's helpful.
So switching the CAD vendors, I guess that tool plugin, that's what abstracts that.
Yeah.
Okay. And then you mentioned architecture and
technology, yeah, those are both plugins that we have. There's no.
What would you say? Where exactly is the technology plugin come to use? And what would you say is the scope of setting up a technology plugin?
Yeah, so there's like a pretty wide range of setting up technology plugin. It's very easy to get GDS out. I mean, very easy. It's pretty straight. Like for a Hammer developer or someone familiar with the tools, it's pretty easy to go from nothing in a file to a plugin that will get you GDS out. And then the hard part becomes cleaning everything up and making sure your designs come out DRC, LBS clean the first time with your tech plugin. And so that involves more iteration. There's certain standard cells that have problems. You might exclude them. There's certain extra commands you might need to run to clean up dangling whatever's, right? These kind of things take time, but it's hard for me to estimate exactly how long it takes for us, but we've gotten several plugins to this level of maturity where you get like a DRC clean design out first.
And I assume when you mentioned architecture or architecture convergence, you're probably referring to the feedback annotations.
Yeah, so our chisel generators have lots of parameters you can set. How many buffers do you want on your tiling crossbars? How deep should your FPU be? All these things that you get a report out of Hammer. It tells you your critical path here or there, or you're having congestion here. Then you feed that back into updating these chisel parameters.
Can you give me an idea of your sort of current user base? Is it mainly university research at Berkeley, or do you actually have people in industry that are regularly talking to you?
So we talk to people in industry quite a bit at our retreats. and there is interest from several of them. I think especially now that we've packaged it up with chipyards so they can, get access that way a little bit easier. But most of our users are in academia still, I would say. But we're like talking to some of our lab sponsors in terms of getting them to try it out and give us feedback. Yeah.
How closely tied is this to chipyard at chisel implementation flow? Is it applicable to like a plain?
So you can use Verilog, plain Verilog going into Hammer. You won't get some of the benefits of these higher level APIs, like that are based on chisel annotations and fertile stuff. But I mean, originally Hammer was separate, and so it still maintains those capabilities of just running on Verilog.
So the power bit, do you guys have power switch plug-in? And also, does it have, do you guys already have low power, like the isolation?
So we have some UPF, CPF stuff, but we don't support isolation cells yet. We don't have that as a feature yet. But we do have like level shifters and things like that, huh?
You guys are planning to do it?
Yeah, we are planning to do that, yeah.
And I think the whole hook system allows you to still use most of the Hammer flow without.
So we have built chips with Hammer that have those features, but there's no API in Hammer for isolation cells, for example. We did the hook system to implement that. So we have a prototype, I guess you could say.
For SRAM, for example, some problem with a lot of SRAM, so you guys, how to control it to inside? I mean, in the regular flow, we can keep it there, but how you guys can control those SRAM dominated flow?
So the way SRAMs work in this flow is there's basically, Chisel generates this configuration, which is a list of all the sequential memories in your design. Then there's a tool called macrocompiler, which takes that and maps that to a discrete set of SRAMs based on your technology parameters. And then that spits out like a Hammer snippet that you include, and Hammer then knows about all your SRAMs that way. I'm not sure if that was the question.
How to plan for the SRAM and how to go around all the DLC and those repeater, those.
Yeah, so
how to control those as well?
Yes, there's settings in your technology basically, or some settings in your technology that help you deal with, how much space you need outside of your SRAM, like how close can they be abutted, that kind of stuff. We're also working on one of those things I mentioned before. John's working on kind of a higher level floor plan description where you can say, put your SRAMs in this box, and then it will, butterfly them appropriately with following the same DRC rules that Hammer knows about.
So which one?
That specific part, yeah. You can, yeah. Okay. Yeah.
So what is the biggest design you have?
So the largest design we did with this was a 7.5 by 7.5 millimeter chip in 16 FinFET. It was 20 cores with 2 different kinds of accelerators and 8 bag generated 28 gigabit per second SerDes, a large multi-level cache, and so there's L3 even, and then a bunch of other like peripheral test chip widgets.
And how long it took
So
placement?
just running the flow itself. That only took like 2 days.
2 days.
It was like, since we had 20 cores, a lot of that was replicated. Yeah.
Do you have anything special for routing channels or top level placement route, or?
We've gotten that request before for routing channels at the top level. We don't have anything special yet. Okay. Thank you.